want you guys to have fun with it. So there you go. Can we read what it says there? Sort of, I guess. All right, yeah, go ahead. Relax. Think about it. So raise your hand if you think you solved the puzzle. Raise your hand if you don't think you have yet solved the puzzle. Raise your hand if you didn't raise your hand. Either one of those questions. All right, so you can stew on this for a little while until Thursday. And we're going to move along, and we'll discuss it on Thursday. Okay? So, the first thing I wanted to talk to you about was to give you a little bit more info on the research projects, which apparently are getting cut off in this slide, but that's fine, we'll manage. If you have no background in sort of the financial matter at all, you might not realize like what these projects are actually about. I want to kind of give you some idea of what these sample topics are. Again, you don't have to choose one of these. You can pick anything you like. But just to give you some idea, right? So the first one is just sort of an exploratory study of the data on people's personal budget and what people spend money on. In this class, we're going to do sort of personal budget as a homework assignment. So some of the, like one data set that you will have is everybody's personal budget, right? And I also want you to go out there to the wide internet and get some data on people's spending patterns and all that kind of stuff, right? And then do some kind of a sort of a basic statistical aggregation of what the patterns are looking like. And maybe for certain categories, you might want to even research what the cost of various things are and sort of put it together and see spending what your estimated costs are, or they're spending more, or they're somehow managing to spend less, right? So that way you will sort of have an idea of maybe where people have trouble controlling their spending, right? Because if you have an idea of what spending should be given what the costs are, and you see that people tend to spend larger amounts, right? And then, well, number one, maybe you forgot something. Like, hey, it looks like people need a roof over their head, right? Or not, but if you think you pretty much covered it fairly well, uh, and yet there is still a discrepancy, that's one area that we all could probably pay attention to as we go along in our future lives, think, try to avoid overspending in this area and that area, right? That's kind of the general idea, nothing particularly fancy. The next sample topic that I proposed for you is to look at historical investment returns by broad investment categories, right? So I'm not saying look at individual assets, but look at sort of index categories, like talk about, bond funds, stock funds, value stocks, growth stocks, whatever we'll talk about what all that stuff is, and sort of see what are the returns of the various investment categories and what seems to be a reasonable mix of investment classes in your portfolio to sort of produce a reasonably stable, reasonably good return over time. Right? So for this project, you'll have to collect some historical return data on these different asset classes, try putting them together in different weights in your portfolio, and kind of see what happens with the returns and variances of your portfolio over time. Right? Third one is to look at patterns of investment returns for individual assets, individual securities. We'll talk later on in this class about the concept of diversification, right? So I want you to examine this idea empirically by actually collecting some data on some assets, putting them into portfolios, and see how that affects your portfolio return relative to the average of the individual assets, right? So again, you will have to collect some data on individual asset return. You don't have to collect the data on like every single asset out there, but just a sort of a good representative sample of the asset. Right? Now let's see if we get out of the full screen mode. Maybe we'll see the other stuff. Or maybe, oh, look at that. Okay. No. Okay, maybe that will do. Let's try maybe changing the font. Well, we can see that. Okay. All right. Next project is to look at insurance, various insurance products. Ideally, what I'd like you to do is to look at the actual, pick some particular area of insurance, maybe it's a car insurance, home insurance, health insurance, right? A liability insurance, anything you want, and look at what the actual structure of these risks is, right? So you might look what is the probability of such and such loss, what is the magnitude of such and such loss, what are all the losses that can be associated with this particular area of insurance, and then see where how the pricing of a particular insurance policy is relating to the expected value of the loss in that particular area, right? Now, of course, we know that if we have calculated everything correctly, we know that the price of the insurance policy is going to be higher than the expected value of the loss, right? Why is that? Exactly. They're not going to sell you stuff so cheap that they lose money on every one, right? And make it up in dollars, right? So they want to, on average, want to make money. So they're going to find the expected losses, and they're going to add some bit of profit to give them a cushion, right? So you know that if you sort of don't forget any interesting risks, or don't grossly under or overestimate the probabilities, it should come out to be the case that the price of the insurance policy is higher by some percentage than the expected loss, right? And so that will sort of give you an idea of what kind of losses you're insuring against, what is the extra premium that you have to pay, right? Because of course, if you go out and get some quotes from an insurance company, which you will do as for this project, they'll tell you how much they will charge you, but they won't tell you how much is their premium relative to their calculated expected loss, right? That's up to you to figure out. The premium could be 1,000%, and you'll never know unless you actually go and look into it, right? So hopefully, if there's competition among various insurance companies, they won't be able to stick to their 1,000% premium for long because competition will drive down prices, right? If we don't know unless we look into it. Right? In general, insurance is it's an interesting area to look at, and we'll talk more about risk aversion in this class, and we'll sort of get more into it. But that's kind of the general idea of this class, right? And there are multiple areas of insurance we can look at. Then the next project is a financial analysis of owning a home versus renting in some particular area. Right? In general, there is a lot of things, a lot of factors involved in the decision. We have to look at the effect of inflation on your rents over time. Whereas, for example, if you get a fixed rate mortgage, that will be a fixed payment. Right? But the money you are saving from the fixed mortgage payment relative to the rent, you could be investing. And so you have to figure out what is the investment rate of return that I can assume on my savings, right? And you can, depending on what you invest in, you'll get different returns, right? Then you have to worry about what's happening with the value of my house, right? Because you're acquiring ownership in an asset. So depending on all these various different parameters, it may come out to be the case that it makes more sense to rent, or it may come out to be the case that it makes more sense to buy the house, right? This is kind of an interesting project because it is a decision that a lot of us will have to think about at some point in our lives, right? And so what better time to do that than a personal finance class, right? And I mean, you're not limited to these. If you think some particular area of finance is interesting to you to research, you can feel free to just tell me about it. Now, I mean, a lot of this information we're going to be covering in the course of, this class, right? But we cannot talk about everything all at once, right? So, you could have seen the sequence of topics in our syllabus. So I like to start with that. We'll look at some financing decisions, we'll look at investments, we'll look at insurance, right? So we cannot cover everything at once. But if you choose a particular topic, we'll meet with your group, personally, and we'll discuss in more detail of what kind of we want to achieve in a particular project, right? So don't worry that, I don't really know anything about investments yet, so I don't want to pick that topic. Well, the point of the research project is for you to learn more stuff about it, right? So if you pick that topic, I'm not going to say, let's just wait until we get to it. Maybe we'll discuss some more stuff. So you kind of get to learn about it earlier than everybody else in the class, if you pick that up, right? Okay, any questions? Yeah? Yeah. I mean, these topics have already been posted last week, but the rest of the slides will also be posted. And I guess I should post the first week's slide. All right, so remember, I did ask you to form your groups and choose your project by Thursday, which is in 2 days. Please think about it, make some friends. If you don't know anything already, pick something that is interesting. Okay? And at the end of the day, I would, if none of this interests you, pick something that does, that is related to finance. I want your research project to be educational, but also interesting. I don't want you to have to say, insurance, it's stupid. Why am I doing this research? Right? And I want it to be something interesting for you. Okay? Alrighty. Let's see. Let's try getting back to presentation mode. Okay, so next I want, it's really important for us all to be on the same page as far as the basic probability and statistics. I know a lot of you said that you have studied some statistics before, some of you said you haven't. So for some of you this will be sort of a review, for others of you this will be sort of a lightning quick breeze through some basics of probability, right? And hopefully it will be sort of interesting to all of us. Okay, so there is no board on this side of the room, so you might have to look with it. So the basic framework is this, all right? The probability of certainty, right? Something that is certain to occur is pretty much arbitrarily defined to be 1, right? Probability 1 is we are certain that it will occur. Now, I mean, it's a convenient number, right? But there is no serious fundamental reason why it has to be 1. We could normalize everything to be probability, 3. That would be certainty, right? It's just that, doing things in the 0 and 1 is sort of reasonable, it's sort of nice, and, historically that's the way it's been done, but like, don't think that 1 is somehow special, somehow a special number that you have to, ascribe special meaning to other than just by convention, right? So, in general, we say, okay, so this is looking at some particular situation, we can say, you guys in the back, right? Look in some particular situation, we can say that we can draw the box, and say that this represents the space of all possible events that can occur relative to our problem, right? So whatever, all sorts of different things can occur, and altogether this is the space of all possible events. And so something in here has to occur, right? So the probability of something in this area occurring is what? What, right? Again, like certainty is 1. So now relative to this total event space, which encompasses the sort of exhaustive list of all things that can occur, we can say, well, what is the probability of some subsets of this event space occurring, right? And so this is where we get into sort of more interesting probabilities. For example, you could say, look, this is some kind of an event. And so we say, well, what is the probability of this event occurring? So based on this diagram, essentially think about if we're going to throw darts randomly into this box, right? Well, we may hire some monkeys for this. Customers would say monkeys for this. The monkeys to throw darts at this box, right? And so the question is, what is the probability that any individual dart is going to be in this little circle, right? And so hypothetically, we can look around, we have monkeys throw monkey darts, and then we're going to say, well, what fraction of the darts ended up in the circle, and that would be sort of the probability that this event occurred, right? That's why we represent the probability of the areas, because we can sort of intuitively grasp, what fraction of the total area is the area of the circle, right? And that's the probability of some event, right? So, for example, maybe a simple binary event would be whether the students will read an assigned chapter from the textbook by the time they come to class, right? And so we can say that if we pick a student at random and we ask them, have you read this chapter? And the student doesn't lie, right? There is a certain probability that he read it, and there is a certain probability that he didn't read it, right? And those two, the simple framework, those two probabilities are kind of mutually exclusive. So, for example, we could say that, this here maybe is the probability that you read, P is good, or PR is the probability, right? The probability that you read, and the rest of it that means is the probability that you didn't read. So the mediation, there are several symbols for mediation. Right? And so you know that we generally have to add up to 1, right? Because they're mutually exclusive events. Either you read or you didn't read. So if the probability of the student having read the chapter is say 20%, that means there is 80% that the student hasn't read it, right? Altogether, they add up to 100%. Right? Anybody have any questions with this? Is it sort of making sense, the basic idea of what is probability, what is the probability of some event? Right? Can you understand that? Okay. Right? The events do not have to be mutually exclusive. Right? If the events are mutually exclusive, it's easy, right? You just say, okay, it's probably, however many events there are, let's say there's another event over here, right? Whatever it is, right? But you can't, either one occurs, or the other occurs, or the third occurs, right? You can't have that both of them occur, both of them occur together, right? So mutually exclusive event, when we see mutually exclusive events, you can right away know that if we list an exhaustive set of mutually exclusive events, the probabilities of all of them have to add up to 1, right? Because it's not possible to work together, right? So somebody give me a nice example of some event with several mutually exclusive probabilities, just so I know that you guys are with me. Okay, right? So dice rolls are one of the canonical set of random mutually exclusive events, right? We have 6 possible outcomes. In the case of a dice roll, we could possibly divide our total sample space into 6 equal variants, right? And one or the other, so the 6 have to occur if we roll the die, right? So the probabilities of all of them together have to add up to 1. Right? So that's, everybody with me? That's a set of mutually exclusive events. Right? Now, that's the basic part. Let's look at the possibility where events are not mutually exclusive. So let's imagine that somebody come up with an example where events are not mutually exclusive. Can you do that?
Maybe like if you're picking a student like at random, you could like talk about the classes and like some students like take 2 of the same classes. I mean like 2 classes and then sample space. You know what I mean, kind of. Like the probability of picking a student with like either like chem or bio, but there's also like a student who takes both of them.
Sure, right. That would be a possibility. I think we're looking at whether a student is taking chemistry or taking biology, whether they can be taking both, or either, right?
That's something old and new. It could be both and nothing.
Okay, so another good one, right? Right, or it could be neither. Anybody else? How about we pick a random person walking down the street? There is approximately a 50% chance that it is male, right? And there is also a chance that the person is, say, a police officer. Or maybe not. Right? Right? So those are, the probability that the person is a police officer is one event, right? The probability that the person is male is another event. But he could be both a male and a police officer, or he could be neither male nor female, right? So when you read it, it's just like when you think think of two things that are not mutually exclusive, and like you're there, right? So I mean, you can pick a desk at random from the population of desks in the United States, right? What is the probability that it has four legs? Probably pretty high, right? Although you can have like a three-legged table, or you can have a five-legged L-shaped desk. Anyway, right? But there's a probability that it has four legs, and there is also a probability that the table surface is, say, yellowish, orange, or whatever the surface is, right? And so and there's a probability that it's both, there's a probability that it's neither, and there's a probability that it's one or the other. And I really, any, just any two things, right? They can be like that, right? Now, here, so if we draw two, if we draw two events that are not mutually exclusive, and once we present them on the diagram, we can draw something like this, right? So this would be maybe the probability. That would be the probability that it has four legs, and this would be the probability that it is yellow. And in this field, this area, where the two overlap, is the probability that it is both yellow and has four legs, right? And of course, what is the rest of this area here? Right, there's a probability that it has neither yellow nor it has four legs, right? Now let's imagine that, let me just give you a simple problem. Let's imagine the probability of four legs is, say, very high, 80%, right? And let's say that the probability that it is yellow is, I don't know, 10%, right? Now, if that is the case, can you tell me what is the probability that it is neither yellow nor has four legs? Yeah?
Is it 10% because they added 290%?
It would be 10% if the two events were mutually exclusive. So it's a trick question, and the answer to that is no, I cannot tell you the probability that it will be neither one, right? So, I mean, it's a good thinking, you're trying to apply what we're talking about, but we know that this area right here, probability of yellow is 10%. We know that this area right here is 80%, right? But there is some overlap. So we cannot say that the rest is the 10%, right? Because some of the 80 and some of the 10 are both covering the same piece of area, right? So, given this information, the probability that it is neither yellow nor has four legs, does it have to be greater or less than 10%? It has to be greater than 10%, right? Because we took away some of this area and overlapped it. And we overlapped the two, right? So without knowing what is the probability, right? The probability of yellow and, which is intersection, yellow and has four legs, we have to know what that is, what this area is, in order to know, how much area of the sample space remains uncovered by the two, right? And so let's imagine that the probability of yellow and 4 is, say, 2%, right? Now, given this information, can you tell me the probability that it is neither yellow nor has four legs? Okay. That's the right answer. Now, what is it? All right, 12 sounds good. Right? Why is it 12? All right, good. There's a few more steps that you needed, but You're thinking it through step by step. It works. Everybody can see why it's 12%, right? Because, you know, this 2% area is covered twice by these two, right? So we don't want to double count it. So we can add these up and subtract 2%. Right? Everybody with me? You mean why this particular thing is 2%? Oh, we just picked a random number. And then let's imagine that the probability that those happen together. Yeah?
I'm the worst person to probability. I'm so confused by that. Why you don't put it in there. I don't get like why you will take it away from me and take it away from them.
Oh, I mean, you don't want to take it away from both, and you don't want to subtract it twice. You only need to subtract it once. Subtract it twice, you need to put one on the back. So, I mean, what you did is right, that's what you did. You took the 2% away from both, so you counted this area right here, right? This circle was a bit cut out of it, which would be, with a 4, right? That would be, this circle is 80%, and this intersection here is 2%, right?
Okay.
So that means that this crescent moon thing is 78%, right?
Okay.
You with me?
Yeah.
Okay. Now let's look at the other guy, the inverted crescent moon, right? So the whole circle in yellow is 10%,
So the 8%.
all right? And so, but you take away the 2 and it's 8,
Okay.
right? So now we want to find the probability of everything. So we know the probability of 4 but not yellow is 78. The probability of yellow but not 4 is 8. So then we need to know what is the probability of everything else. Well, what's the probability of yellow and 4, which is 2. And the rest must be where there's neither yellow nor 4.
Okay.
Right? So
Thank
if
you.
we subtract 2 from both, we have 78 plus 8 plus 2 plus whatever remains has to add up to 100. Right? Okay? Everybody with me? A good question. Probably some of those students who are probably benefiting from this discussion. Okay? Now, everybody on the same page? Any other questions? Okay. All right, so this is the basics of probability, right? And this is the core bedrock concept underlying a lot of statistical thinking that we'll be doing in this course. So it's important. I really wanted to kind of make sure we have this as a common shared ground to build up. Right? Now, let me talk about the concept of independence. Right? So what does it mean when two events are independent? Well, the colloquial meaning of the word independent sort of is, right? But it has a specific mathematical meaning, right? Yeah?
We have to move on with the other
Okay, I'll buy that. You got something else?
I was gonna say basically the same thing, that one event's happening doesn't impact the other.
All right. So we can define. The independence of events in terms of conditional probability. But I don't necessarily want to go into the idea of conditional probability, right? But we'll probably go there anyway. So the idea is that given that a certain thing, if a certain event is true, the probability that the other thing is also true is not affected by the fact of the first one, right? So in case of the 4 legs and the color yellow, we could say that the probability, if we pick a random desk and it has 4 legs, let's say we have 80%, right? And the probability that if we pick a random desk and it has the color yellow is 10%. So independence means that if we pick a random desk and observe the number of legs on the desk, and lo and behold, it has 4 legs. And then we have to say, well, now we're going to go and observe the color of the desk. What is the probability that the color of the desk is yellow? Right? Given that we already know that it has 4 legs. If the events are independent, what is the probability? It is 10%, right? Because the probability of the color is not affected by the fact that we already know the number of legs. right? And of course, it has to go the other way as well. If you pick around the desk and first observe the color and say, lo and behold, it is yellow, right? And then we say, now we're going to observe the number of legs. What is the probability that it has 4 of them? What do you say? 80%, right? So independence is sort of a symmetrical phenomenon, right? Because given one, the other probability doesn't change. Given the other, the one probability, right? So how can we represent this in terms of this diagram, right? So, and so we want to know what is this area where the circles overlap if it is the case that these two events are independent. Alright, so let's imagine that we observe, alright, so let's imagine that we observe that the disk has 4 legs. And so we know that by independence, it must be the case that if we observe the color, the probability of that color being yellow is 10. So what must be the size of this area? Yeah. Why is that? Right. Excellent. Right, everybody heard that? Right? Well, in order for the probability of it being, yellow to be 10%, given that we observe the number of legs, that means that this shared area, where the desk is both yellow and has 4 legs, has to be 10% of the area where the desk is just 4 legs. Right? Everybody following me here? You mind that? Alright, so we have observed that it has 4 legs, right? So now we can discard everything else and just focus on this space, where it is true that the desk has 4 legs. And so now we're saying, what is the probability that given it has 4 legs, it also has the color yellow? And we want that to be 10%, because it is independent. So given that we observe the 4 legs, the probability is still 10%. So in order for the probability to be 10%, the size of this area, the size of this overlap, has to be exactly 10% of the size of the circle. Right? So what is 10% of the size of the circle? It is 10% of 80, which is 8. Okay? Yeah? Well, we said that assume that these are independent events. So that means that given that they're 1, the probability that the other is 2 doesn't change. Right? That's why we said that once you observe 4 legs, we still know that the color is randomly distributed and the probability that it is yellow has to be still 10. Because the probability that it is yellow changes after we observe the number of legs. That means they're not independent of it. Right? The probability of color is affected by the number of legs. But we want it to be unaffected, right? That's the meaning of it being independent. Right? You buying that? Okay. All right. Anybody else has any questions? Is this clear? Everybody on the same page? Okay. Now let's write this down mathematically. Right? What do we find out? Right? We know. Like let's work in terms of the yellow boards that we have here. Right? Right, we know that the probability of the desk being yellow by itself, we just pick a desk at random from the population of all desks, is 10%. It has to be equal to the probability that if we observe that the probability, of the, if we observe that the desk has 4 legs, then within that space, the probability that yellow is the same as before. Right? So how do we denote the probability that it is yellow given that it has 4 legs? Right? Well, how did we find the probability? We said we're getting the probability that it's yellow and it has 4 legs as a ratio of the probability that it is it has 4 legs. All right.
No problem.
Yeah, I guess you guys are better. Yeah, next time I go over to change the slide, I'll make sure to record what the slide is there. I guess you don't even need to record the slide because I'll post it to Blackboard. Okay. It's not too far. You think the video will show what the
Should I bring it closer?
Yeah, it probably would be helpful then, since we're kind of working on this side of the room. That would have been one sad video, for sure.
Yeah, looking at that the whole time.
Yeah, with a faint voice talking in the background.
All right, looks pretty good to me.
Okay, can you see the board there? Yeah, I guess so. Yeah. Okay. Actually, maybe put it on, I don't know, can you maybe put it on this, because there is a reflection from the windows coming in.
Okay.
Whereas here, there is no reflection. So, I'll put it this way.
Yeah, we're looking good. Don't let me slow you down.
All right. Okay, so can everybody see this, right? So we said that this has to be the same as the independent, as the sole event probability, right? So this area of this region divided by the area of this region has to be equal to the probability that it is yellow for it to be independent. Right? Everybody with me? Have you made the leap from the graph to the math?
Wait, say that one more time.
Okay.
Is that yellow?
So this is right. This is the this is supposed to be yellow. Yeah, I guess this is an unfortunate choice of events because the 4 sort of looks like the Y. Okay, let's say that it's we can change the color, right? Maybe let's call it green. Right? Okay, so let's say that it is green. Right, it looks very different. So here is the Y, here's another Y. Right, it's going to be green. It's going to be green. Right. This is going to be green. And this is going to be green. Okay. Right? A little adjustment, right? Now the probability that this green is 10%. Okay, right? So you see here, right? We said that for it to be independent, once we are within the space of that it has 4 legs, we say the probability that it is green, given that it has 4 legs, should be equal to just the probability that it is green, which is this one, relative to the rest of the space. So how do we define that? We said, well, we take this area and divide, which is green and 4, right? The probability that it is green and has 4 legs, divided by the probability that it has 4 legs, that is what we observed, has to be equal to just the plain probability that it is green, which is 10%. Right? Okay, everybody with me? All right. So let's give it a little rearrangement. Green and 4. Multiply both sides by the probability of 4 legs, and we see that the probability that it's green and it has 4 legs is the product of the 2 probabilities independently of one another. Right?
Yep.
Okay, everybody with me? Are you buying that? Does anybody want any clarification?
This shows that it's independent.
Right, so this relationship, you can write it either way, it's the same, right? It's the same equation, just rearranged. This is the mathematical definition of independence, right? The 2 events are independent if their joint probability, that it is one and the other, is the product of the individual probabilities. right? And it will also come out to be the case, if that is the case, that the conditional probability is equal to the unconditional probability, right? So depending on how we write it, we can talk about it in different ways, but it's the same mathematical relationship, right? Everybody with me? Okay. So for those of you who knew statistics and probability, is this sort of review, or is this like new stuff? Review? Okay, that's good. Good to know that they teach some good stuff in statistics. All right. So now, so based on this relationship, you remember when we discussed throwing a coin 3 times, and we said, what is the probability of getting heads, a tails, and a heads, right? Well, it is, probability of getting heads on the first one is half. Probability of getting a tails on the second one is also half. The probability of getting a heads on the third one is also half. So that means the probability of that particular sequence is going to be half times half times half, which is
1/8.
1/8, right? So how do we find that? Well, this is basically the relation that we had. The probability of one event and the other event and the third event is the product of the 3 individual probabilities, right? This extends in a pretty straightforward way to multiple events, right? The probability of, green and 4 legs and 30 inches high, or whatever, right? Assuming they're all independent, it should be the product of those individual probabilities. Right? Make sense? Okay. Now, let me grab a little bit of water while this talking. So we're almost down to the fourth item in this slide. The whole goal is for us to get to the concept of a probability distribution, right? So before we get to distribution, we have to go from events to random variables. Right? So what is a random variable? Come on, you guys. You took statistics, didn't you?
I did.
Oh, I mean, I'm not talking to you. I'm talking to the guys who did take it, right? You have, you have plenty of excuses, not to know this stuff. That's fine. And this course doesn't have prerequisites, so I'm covering whatever we need to cover, so we're all on the same page. Don't feel bad about it. You probably know other stuff that will be useful at some point. All right. So what is a random variable? A random variable is essentially some kind of a aggregation of events that produces a numerical output, right? So for example, let's say we talk about throwing the coin 3 times. It's like it's an easy way to talk about these things, right? So a random variable could be the number of heads in your 3 throws, right? So what are the values that this random variable can take?
0, 1, 2, or 3.
All right, excellent. Everybody can see that? It goes from 0 to 3, right? Stopping at 1 and making a hop at 2. All right? Let's get this thing. Right, so a variable is a way to aggregate some group of events, right? So remember when we talked about throwing the coin, we had 8 possible outcomes. Are you raising your hand? You're just holding
Sorry,
it.
no.
Okay. Right, 8 possible outcomes. We had heads, heads, heads. We had heads, tails, heads, tails, heads, tails, heads, heads. And then we had heads, tails, 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 heads, tails, 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 heads, and tails, tails, tails. Right? So these are all, all the possible outcomes. And we know, given our discussion just there, that the probability of each one of these outcomes is exactly 1/8, right? They're all equally probable. Now we create a random variable that, by some rule and mechanism, aggregates some of these events into a numeric outcome, right? So our example was, and by the way, you can see why I don't use the example of 4 coin tosses, because I'd have to write down a whole lot more outcomes. Namely, how many?
16.
16. Okay. With how many letters in each?
4.
Okay. Just making sure you guys are paying attention. Right? So we know this now. Now let's say we have a random variable that says the number of heads, right? So we're going to be aggregating these events, right? So we can say, what is the probability that there is 0 heads?
1/8.
Right? 1/8, because it only happens in one of the possible outcomes, right? What is the probability that there is 1 heads?
3/8.
Right, so what do we have? We have 1 head here, 1 head here, 1 head here. 3/8. Okay. And what is the probability that we have 2 heads?
Also 3/8.
Also 3/8, right? These 3 possible outcomes. And finally, what is the probability that we have 3 heads?
1/8.
1/8.
All right. And what is the probability that we have 4 heads?
0.
0.
Okay. And 5?
1.
Right? So this is a random variable, right? And it takes on certain values with certain probabilities, right? The concept of a probability distribution is precisely that, to look at what are the possible values and what are the probabilities that the variable takes on those values, right? If we were to graph this probability distribution on some kind of a graph, here we have the outcome, we'll call it X, and here we have P, the probability, right? It goes from, 0, 1, 2, 3. So shift them all to the side so the axis doesn't interfere, right? And have 0, 1, 2, 3. And so if we graph it, it's kind of like a step function. We have 0, the probability of 1/8, right? We have 1 with probability of 3/8, 2 with probability of 3/8, and 3 with probability of 1/8, and everything else is 0, right? Okay? And so, given any kind of space of events, we can construct all kinds of random variables that take on values based on aggregating those events in some fashion, right? And then those values will have certain probabilities as a result, right? And then we can discuss what the probabilities are, and depending if something is dependent on the value of the random variables and kind of payoff, we can talk about, the desirability of whatever the payoff structure is. That's kind of getting a little further ahead, but that's kind of, so we want to know, the probabilities of things happening, because it's kind of important as far as deciding how to act relative to those events, right? Okay, any questions? Are we okay with the random variable approach? Okay, good stuff. Now, let me talk to you about some common discrete probability distribution. But a discrete probability distribution is where the variable takes on only certain values, right? This is a discrete random variable because it can only take integer values. Right? A continuous random variable can take on a continuum of values, right? So there is no particular points on the axis where it can take. It's just a smooth continuum that it can take a value. For example, if you think of the distribution of human heights, right? There is no, human heights do not come in integer inches or integer centimeters, right? Humans have continuously variable height. So if we were to draw some kind of a probability distribution, right? So look at that. If we were to draw some kind of probability distribution for human height, it would probably look kind of like that, right? We are probably all familiar with the concept of the bell curve, right? The normal distribution. Right? The normal distribution is an example of a continuous distribution where the variable can take sort of any kind of values in some range, right? Now, I'm not going to go into that. Right, so discrete. So there is really like an easy parallel between like the discrete and continuous distributions, right? Both ways, you know, we have some probability, right? We have the value, and we can measure sort of what is the probability that the random variable will be in some place, right? So let me talk about a couple of discrete distributions. We talk about a couple of discrete distributions. Let me talk about one discrete distribution. Then we'll talk about some basic combinatorics. That was the previous slide. And then we'll talk about the other discrete distribution, which depends on our discussion of combinatorics. Right? Okay. So that's a very, sort of bedrock core distribution that is, it's commonly seen in statistics. It's called the Bernoulli distribution, right? So what is a Bernoulli distribution? You the guys who. Yeah.
I've never heard that word before, but is it like a frequency diagram?
I mean, it's a very simple distribution. So it doesn't really have. It's not really going like that. Okay, I'm disappointed now in your statistics classes. Okay, so Bernoulli distribution is named after a statistician who was named Daniel Bernoulli, and he did like a lot of important mathematical work and also like some science work. And so a Bernoulli distribution is very simple. It says we have a binary outcome, right? The random variable can take only two values, 0 or 1. Or you can really pick any two values. It doesn't matter. 0 or 1 are commonly chosen with certain probabilities, right? So if we say that some outcome is distributed as a Bernoulli random variable with probability p, right? We could just say that some variable is distributed as this is the tilde is distributed as symbol. It's distributed as Bernoulli with probability p, right? So for example, the coin toss is a Bernoulli random variable, a single coin toss, with probability of 1/2, assuming it's a fair coin, right? So because the 0-1 outcomes on the coin toss are the heads and the tails, and we can arbitrarily denote the heads as a 0 and the tails as a 1, or whichever way, right? And it has the probability, right? The probability of landing on one side or the other, right? And so for a fair coin, the probability is p. So if we were to draw the distribution for this Bernoulli random variable, it would be 0.5 here, 0, 1, all right? That's it. That's our Bernoulli random variable is probability half. Now let's imagine we had like a loaded coin that came up on heads 80% of the time, right? That would also be a Bernoulli random variable, right? And it will be with probability 0.8, right? The probability would be 0.8, right? Canonically, the probability is the probability of getting the one outcome, right? So it's basically you can denote whatever outcome you want as 1, right? And then model it as a Bernoulli random variable. Okay? Everybody with me? Is this making sense? Right, and so if we were to draw this, right, we would say that here is 0.8, right? The probability 0.8 here, and the other probability would be what? 0.2. Okay. I'm glad you guys are paying attention. Right, so that's all there is to like a Bernoulli random variable, right? It's a binary outcome, 0, 1. It has a certain probability of coming out on 1, Okay? Not very interesting, but we have a much more interesting distribution called the binomial distribution, which arises out of the sum of Bernoulli random variables. And before we go on to talk about the binomial distribution, let's go back to this slide. So how many of you are familiar with the concept of a factorial? How many of you are not familiar with the concept of a factorial?
It's
Okay.
denoted by the exclamation point, right?
Yes. So what does a factorial mean? The exclamation point.
It's the sum of that number and all the numbers that are below it.
Integer.
Not
Or
quite.
The product.
It is the product.
Yes.
Right? It is the product of all integer numbers at or below that particular number. Right? So this is just the basic definition from like I don't know, when did you first encounter factorials? Like high school, right? Middle school, who knows, right? Right, there's nothing fancy about it. It's just a definition, mathematical definition of a particular operation. And the reason we're talking about it is because it will come in handy as we discuss permutations and combinations that in just a little bit. Right? Okay. So, let's say, I can ask you what is 4 factorial, right? A factorial is denoted by an exclamation point. Alternatively, you could just write factorial 4, the same thing, but, writing that is kind of a pain. So that's why, that's the reason why a lot of the mathematical notation is developed, so you can avoid writing words for all these things. There's, writing words, it takes so much longer. So, 4 factorial. What is it?
24.
Okay, why is that?
Because 4 multiplied by 3 by 2 by 1 is 24.
Okay, good. So everybody with me? Right? Okay. How about 5 factorial?
120.
All right, why is that?
Same thing.
Because 5 and all the numbers below it multiplied together are 100.
Or 5 times 24, right? So 120. The point, factorials. The one thing you should realize is factorials grow really, really fast, right? So if you think that 4 factorial, it's reasonable. 5 factorial, it's a reasonable number. If we go into something as small as 20 factorial, how big is that?
Really big.
Very, very, very big, right? Not even going to count the zeros there, but it's something on the order of like quadrillions or something like that, right? Really large. Okay. So listen, some interesting properties, of course, is that factorial of x is x times the factorial of x minus 1. Right? So you can see that factorial of 5 is 5 times 4 times 2 times 3 times 1, which is the factorial of 4. Right? So this is like a basic basic property. Maybe it'll come in handy, maybe not. Right? Okay, so this is the idea of the factorial. Okay? All right. Now, armed with this information, let's look at the concept of permutations. What is a permutation? Anybody familiar with that?
Sounds familiar.
All right, that's a plus. Okay. So a permutation is the number of different ways you can rearrange a certain number of items, right? So for example, if I give you 3 numbers, 1, 2, and 3, and I ask you what are the different ways you can rearrange these 3 numbers in order, what are you going to tell me?
Go through the list.
You might go through the list for these, but what if I give you 10 numbers? probably won't want to spend several years of your life going through the list, right? We're going to talk about sort of a general purpose mathematical way to figure out the number of those permutations, because that will come in handy as we discuss the binomial distribution. Without not spending too much time, can you tell me how many ways we can arrange the three numbers?
6.
6. How did you figure that?
3 factorial.
As it happens, it's 3 factorial, right? Now, why is it 3 factorial?
Because there's 3 choices you can use for the first one. And then once you use one of those, there's only 2 for the next one. And then once you use one of those, there's only 1 for the next one. So you multiply them all together.
Excellent, precisely. Right, everybody hear that? Right, here is where the factorial comes in handy, right? Because we're looking for arranging these 3 numbers in many different, like in all sorts of combinations, all sorts of permutations, that is, right? And so we say, okay, I have 3 bins to fill with numbers, right? So as I'm working on filling these numbers, I'm going through all of the combinations. So when I fill in the first bin, how many choices do I have for the first bin? Well, that's 3, right? Because I can pick either 1, 2, or 3. So I'll place a number in the first bin. Now, for each choice of number that I place in the first bin, how many choices of numbers do I have to place something in the second bin?
2.
Well, that's 2, because I already placed one over here, and we're not allowed to repeat them, right? That's the idea of permutation, right? And so here, now I place 2 more, I have 2 more possibilities for each one of the first one, right? And then after I place the first 2 spots, how many choices do I have left for the third one? Just 1, because I already placed 2 out of the 3 numbers, only just 1 remains, right? And so, place a third number. So how many possible ways can I do this? Well, I have 3 different ways to pick the first one, right? Then for each of these, right? So there's, right, so let's say, 3 different, right? So here is 3 different ways to pick the first one. For each of these, I can pick 2 different ones, right? And then for each of these, I have only 1 more choice remaining. And so by using sort of this decision tree thing, we can enumerate all the outcomes, and we have 6 of them. Right? Everybody with me?
Yep.
Right? You buying this? And so, of course, you can see that as a result, by doing this, this is 3 times 2 times 1, which is 3 factorial, right? And so if I ask you how many ways can you rearrange 10 numbers or 10 objects of whatever kind, right? What are you going to say?
10 factorial.
10 factorial, right? It doesn't matter what it is, it's 10 factorial, right? It's a large number. So you don't have to actually enumerate all the outcomes once you see that there's a pattern to how many outcomes you can produce. Okay? All right. Now, let's see, so this is the basic idea, right? If we're looking to have, rearranging some numbers, that's our idea. Now there's another related concept, is sort of a partial, partial permutation, right? And the question might be, how many ways can you choose k numbers out of a population of n numbers? All right, let's imagine we have we have 10 numbers, right? So, okay, let's start with 0. And we'll have 11. Right, 1, blah, 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 10. All right, so we have 10 numbers. All right? We could start with 0 and then 2, and then 9. Then we have 10 objects. And I might ask you, how many different ways can you pick 3 numbers from this population of 10? So what do you think?
10 times 9 times 8. Does that work?
Exactly, right? Because when we're filling in, what we need is we need to fill 3 bins with numbers, right? And so when we, look at, we can think of building the decision tree, or we can just. So how many choices do I have for the first one? Well, 10, because nothing has been taken yet. So I can start 10 different ways, right? So I have 10 possibilities for the first one. After I have picked one for the first bin, how many choices do I have for the second? I have 9 different choices for each one of the starting points, right? There'll be 9. And finally, after I've picked the first 2, I have 8 choices for the third bin, right? So the total number of these partial permutations is 10 times 9 times 8, right? Everybody with me? Anybody have any questions so far? Is this clear? Okay. So, this is 10 times 9 times 8, yeah?
It's just a personal thing. I got 10 minutes to get the James off. Can I just go?
Oh, wait, what time is it?
12:03.
Yeah.
Class.
Oh, what's it supposed to run to?
5.
Oh, 5? Well, I mean, if you need to go, you can go, but I'm going to use my 3 minutes, damn it.
I'll use the video.
Okay.
Sorry about that.
Yeah, that's fine. Alright, so, this is, 10 times 9 times 8, it is not a factorial of 10, right? Because that would be 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, right? But we can write this down as a partial factorial, and, or, right, in general, so 10 factorial is 10 times everything. If we divide 10 factorial by 7 factorial, what do we get?
7.0.
We get 10 times 9 times 8, right? Because 7 factorial is, see you later, is 7 through 1 multiplied together. And here, 10 factorial, we have 10 through 1 multiplied together. So everything down to 7 cancels out, and we end up with exactly that. Right? So again, it's a nice and convenient way to write down this sort of partial factorial as a ratio of 2 factorials. Right? So in general, if we write down the number of k permutation of population of n, see you later, right? We'll write down n factorial over n minus k factorial, right? And what we'll end up with is just basically the head of the factorial. Yeah.
I have an arbitrary question.
Arbitrary is good.
It's not like relevant to our discussion right now. For the project, are the groups of 3 rigid? Because right now I have a partner, but I don't have a
Same here.
I mean, it's fine, but that means that some other people have to choose some other topics. But I'm not. I mean, generally, like I chose groups of 3, kind of for the reason that we'll end up with approximately 6 groups, and that means we don't have to spend too much time having like everybody present something, right? And then we have. Presentations are fun, like you get to learn something, but if I have 10 of you, we'll have to use like 10 classes to do it, which will take a lot more time.
Okay.
I don't know, ideally, you may find the third.
Okay.
If you're like absolutely positive you cannot possibly do it, that's fine.
Okay.
Like you can announce your empty spot on Blackboard. You can use email all students function. You just say, I such and such and some other guy are looking for a third group member.
Yeah.
Would anybody like to join us? First come, first served. We're really smart. Run that. Or something like that, okay?
Let everyone fight over us.
That's right. Okay, so we haven't gotten quite to the binomial distribution, which was my goal. But that's fine. We are setting important boundaries.
Next time, if you want, there's an outlet right here.
Oh, that might be a little smarter.
Yeah, I don't mind it.
This thing doesn't bounce, so that would be a problem.
Or you can move the table next time too if you want.
Okay.
By Thursday.
Oh, yeah.